Hi students, welcome back to our course e-learning chemistry classes. Today let us start the session number 3030 of stoichiometry chapter, and where the concept of equivalent weight. From the past two sessions, almost 2.5 sessions, we are discussing about equivalent weight. In the previous session also I have discussed how to estimate the equivalent masses of substances involved in a particular reaction. Let us continue that. Let me continue that. And today, please concentrate. Iodine, sodium thiosulfate into sodium iodide and sodium tetrathionate, Na2S4O6. This is sodium thiosulfate. This is sodium, I am writing the name also students, tetrathionate. Both the structures are given while explaining the oxidation number concept to you. Okay, let me calculate the equivalent mass of both the reactants here. Here iodine is 0. Here sulfur oxidation state, because sodium and oxygen nowhere changing, because sodium is sodium alkali metal, it is always +1 only, so oxygen -2 on both sides linked. For sulfur it is, we calculate +2.0. Here for iodine it is -1. Here for sulfur it is +2.5. This already all these calculations we did in the previous sessions. Okay, now let me estimate for iodine. Equivalent mass of iodine. Formula mass, it is molar mass, usually represented by mg. What is n factor for iodine here? If you observe 0 to -1 for in molecular formula of iodine, it contains 2 iodine atoms, so total change you should consider it is 2. Similarly, for equivalent mass of sodium thiosulfate, formula mass M divided by n factor. Let me estimate. Change here for one atom is 0.5. But how many such sulfurs are there in the reacting species? 2 sulfurs are there. So into 2, that is 1. So equivalent mass is equal to molar mass in the case of sodium thiosulfate, which is involving in the reaction with the iodine. And this is not balanced equation, unbalanced equation. Oh, already I told you, it is not necessary in all the cases to estimate equivalent masses for the balanced redox reaction. No need of balanced reaction in all the cases. Only a few cases are there. In such case, at any cost we need the balanced equation. Then only we can easily find out n factor, and then only we can easily calculate equivalent weight. So for many reactions no need. So this reaction is very important reaction, will be useful for us in many aspects, in many areas of entire 2 academic year syllabus, because it involves iodometric titrations. There is a concept, in that concept, which is very, very useful reaction, and equivalent masses and corresponding n factors of reactants also very important here, and please note it down carefully. And after that, let me go for one more approach here itself. You concentrate, you will write, I will write also, no problem. Take phosphoric acid, it's a tribasic acid, it can donate 3H+ ions under dilute conditions. Okay, let me assume dilute conditions, say for example for some time. Let me write down some reactions here. Okay, please concentrate. I am writing reactants here. Please concentrate. Okay. Let me write down all the reactions here. Meanwhile, it is copy down anything that you can tell. So it reacts with 2 modes. It forms Na2HPO4 plus H2. And if it reacts only with one molecule of sodium hydroxide, it is generally H2PO4 plus H2. Now in all the three reactions, these are all very simple acid-base reactions. Anybody can write, even you can also write now. Here what exactly we have to discuss with respect to our equivalent mass is, phosphoric acid is a tribasic acid. Three hydrogens are neutralizable hydrogens by any corresponding base. Right. Here I have taken only 1 mole of sodium hydroxide, and second reaction 2 moles and third reaction 3 moles. While I have taken 3 moles, all the three hydrogens are neutralized. So equivalent mass of phosphoric acid here is m by 3 you can write. Here in the second equation I have neutralized out of 3 hydrogens only 2 moles of NaOH I have taken, means 2 moles of H plus ions are neutralized. So for this you can write equivalent mass as in this particular reaction acid as m by 2 only. Here only one hydrogen is neutralized because I have utilized only 1 mole of OH medicines in the form of sodium hydroxide. So equivalent mass is equal to its molar mass. So all the three are acid-base reactions involving the same acid, phosphoric acid, but cases are different. Up to how much extent of neutralization it is going, it is involving, it is participating. That is most important here. Here, out of 3, how many hydrogens are neutralized, that depends, and that particular aspect decides the n factor, and finally we have to decide it equivalent weight. Please note it down. This is one important approach, especially not only for phosphoric acid, any polybasic acid or any polyacidic base, while it involving in acid-base neutralization reactions. Based on the extent of neutralization, we can fix its equivalent mass. Please note it. Nothing but simple acid-base reactions, students. Now, let me go for one more concept based on equivalent weight. Please write down along with me. That is, I am writing here. Principle of, write down, principle of gram equivalent. Keep the heading, students. Very, very important area it is. Useful for solving many numericals within fraction of a minute. Right. Principle of gram equivalence. Let me explain with example. Then I will dictate the statement. I have taken 2 reactants, barium chloride and sodium phosphate, and gives barium phosphate and sodium chloride. Right. 3 BaCl2, BH3PO4 twice, 6 moles of sodium chloride. This is the balanced chemical reaction. I can write like this. 3 mole of barium chloride always combined with 2 mole of sodium phosphate forms 1 mole of barium phosphate and giving 6 moles of sodium chloride. This is as per balanced stoichiometric equation. Anybody can write. But if you apply principle of gram equivalence to this reaction, you consider 1 equivalent of barium chloride should combine with 1 equivalent of sodium phosphate should form 1 equivalent and 1 equivalent. That is the meaning of principle of gram equivalence. Let me explain now. According to this principle, the reactants always reacted in terms of their equivalents and forms products always in terms of their equivalents only. And according to this principle, moles are only useful as representation of paper and both. But in the reality, according to this principle, in the reality, reactants always react in terms of their equivalents and produce products only in terms of their equivalents. That is the reality according to this principle of Gram equivalence. It means our final conclusion is number of moles may be different for different components present in a given chemical reaction, but number of equivalents of a chemical reaction for all the components are always the same. It means if you start with two equivalents, it combines with two equivalents, it forms two equivalents and two equivalents. No doubt. If you start with 100 equivalents, you should combine with 100 equivalents and forms 100 equivalents each of the products. That is the meaning of the principle of Gram equivalence. Moles may be different, but the equivalence should be same for a chemical reaction throughout with respect to all the components, both the reactants and as well as the products. That is the meaning, principle of Gram equivalence. Now you can write down, I will repeat 2 times the sentence. You write down the statement, students, concentrate. In a chemical reaction, the reactants always react in terms of their equivalents and forms products only in terms of their equivalents. I will repeat the statement, students. In any chemical reaction, the reactants will react in terms of their equivalents and forms products also in terms of their equivalents. Now coming to the explanatory part once again. Meanwhile, please write down this example. In a chemical reaction, the moles of reactants and products may be different, but according to principle of Gram equivalence, the equivalents of all the components are always the same for a chemical reaction. That's what I have written actually here while I am explaining to you about the principle of Gram equivalence. One equivalent, one equivalent, one equivalent, one equivalent. Equivalence number should be same throughout. For all the chemical components involving in reaction, that is in terms of reactants and as well as products. So equivalents may be the same, but moles may be the different, but equivalents are the same. That is nothing but the principle of Gram equivalence. Now, I am going to conclude this particular principle with one important application. See, I am writing number of Gram equivalents. Number of Gram equivalents is equal to number of moles into n factor. Number of moles are gram moles. Instead of moles, you can also write gram moles. Gram moles are moles. Simply you can write gram equivalents are equivalents. If you miss gram also, no problem. You can simply write, no problem. Gram equivalents are equivalents. Gram moles are moles. Both are same. So for a substance, number of gram equivalents is equal to number of moles into n factor. That is the final conclusion of this principle of Gram equivalence. By using that particular approach, we can solve many numericals which cannot be easily solved by using normal approaches what we learned up to now. If you write down this, I will go for that particular approach. I have already teach you that many chemical reactions need not require balanced chemical reaction to get the equivalent masses and factors. But for some chemical reaction there is a need of balanced equation. Now I will go for that set of equations to estimate n factor and then to estimate equivalent weights of such type of substances by using this particular principle, that is principle of gram equivalence. By using this technique, number of equivalents is equal to number of moles into n factor. If you know the moles, if you multiply that with n factor, you will get equivalents. If you know the equivalents, if you divide with n factor, you will get moles. By using that relation, now let me go for next type of approach based on the calculation of equivalent weights. Okay. Okay, so let me take one first equation. Let's go. Get ready? I'm going to apply this concept. Already we have discussed two equations of this type, where balanced and redox reactions, which we cannot follow normal rules by estimating oxidation numbers, increase, decrease, reverse and everything. In some cases we cannot solve directly. So for such type of things, I am reminding once again to you. Right. Concentrate. Here it is +4, -1, for chlorine 0, for manganese +2. And here for chlorine is -1 again. Okay, no doubt the manganese is very clear. One reactant and complete all the manganese go in the form of only one product. So simply you can assign oxidation numbers, change in oxidation number, whole n factor for manganese dioxide in this reaction is 2 fixed. But coming to this, there the problem is. Some chlorine is going as it is, -1, -1, but some chlorine is oxidizing. No stoichiometric coefficient. So how can we decide how many chlorines are oxidizing and how many chlorines are not changing? We don't know. So for such type of things, we need a balanced chemical equation to find out n factor actually. Okay, let me write the balance. This is the balanced equation now. So for HCl, 2 says 2 chlorines are undergoing oxidation, 2 chlorines are not changing. Then also we cannot estimate. You cannot take that only change is 2 and 2 gets cancelled. No, it becomes wrong. N factor is not 2 for this chlorine. No, no doubt. So now I can apply the concept of principle of gram equivalence. What exactly we learned just now. Now let me explain that. Here I am writing 1 mole manganese dioxide is equal to 4 mole HCl as per balanced equation. Now I am changing these moles into equivalents. How you get equivalence? As per the principle of gram equivalence. Number of equivalents of a substance is equal to number of moles multiplied by n factor. Oh, and not only that, the actual principle also we can apply here. Moles may be different, but equivalence should be same. I am writing according to principle of gram equivalence. Simply I am writing equivalence of manganese dioxide should be equal to equivalence of HCl. Numbers should be same according to principle of gram equivalence. Moles may be different. Here 1 mole is equal to 4 mole HCl, but equivalence should be the same. Now, how you get equivalence of manganese dioxide? Moles multiplied by n factor. How many moles are there? 1. 1 into n factor. For manganese dioxide is 2. I have fixed here. 2 is equal to. How will you get equivalence? Moles 4 into n factor. That's what I cannot fix there. That's what I should find out now. Now N factor for HCl is equal to 1 by 2. Now I can calculate the equivalent mass of HCl. Here I can write, friends, concentrate. Equivalent mass of HCl in this particular reaction. Formula mass 36.5, we know HCl divided by N factor 1 by 2, that is 73. Look, equivalent mass is more than that of formula mass. Generally, from the beginning of equivalent masses, by using all the formula approach, what exactly we learned? Equivalent mass is equal to formula mass divided by factor, formula mass divided by factor. So, equivalent mass may be always less than molar mass. We may be in that illusion sometimes. No chance. Equivalent mass of substance may be more than its formula mass also, because it depends on the context in which way that particular substance is reacting in a particular reaction. It decides its N factor and it decides its equivalent mass. Here you got equivalent mass double of the formula mass of HCl. So equivalent mass of a substance may be its molar mass or maybe more than its formula mass based on the N factor. Please note it down. It's very important approach. Finish off this, I will go for 2 more examples based on this. Please note it down. Very important. Don't forget about it. While balancing redox reactions, this type of complicated reactions at the end of that succession we have discussed. Let me remind it once again. Right. I am writing the equation. HNO3. Aluminium nitrate. You are already having this equation, fully balanced equation you have. Instead of multiplying left side, we have multiplied on right side and we have balanced already this. I am not going to explain all those things once again. I am going to apply the concept with respect to equivalent mass here. Let me write down the answer coefficients first of all. 8, 3, 9. Let me check out. Only with respect to one element I will check. 30 hydrogens, 12 plus 18, 30 oxygens, 90. 3 3s are 972, 72 plus 981, 81 plus 990. Okay, balanced equation, no doubt. We have already balanced this. Right. Now, my target is, I want to calculate the equivalent mass of nitric acid in this. That is my target. I don't know the N factor directly, because for aluminium you can write directly, change is 3. Directly you can write. Directly. But for nitric acid, only some nitrate, only 3 nitrates are changing, remaining 27 nitrates are going as it is towards the products side also from the reactants side. Okay, now let me apply the principle of Gram equivalence to this equation. So based on that I have to write equivalence of aluminium should be equal to equivalence of nitric acid. How many moles are there? 8. N factor is 3. Because changing into 3, all the aluminium goes only into one compound. Here, equivalence of nitric acid. Moles I know, but I don't know the N factor. First let me estimate the N factor. 10, 4, 5. So N factor is equal to 4 by 5. 4 by 5. 4 by 5. Now, equivalent mass of nitric acid. What we are doing? Formula mass divided by 4 by 5. That is 5N by 4. So, this is based on the application of principle of gram equivalence, especially not only this type of reactions. Finally, you can use a normal simple redox reactions also. You can apply the same concept within the less interval of time. You will get the n factor. Once you get the n factor, immediately you can go for the calculation of equivalent masses of any reactant involving in that particular reaction. So only two final conclusions that one should remember here, very very important. In a chemical reaction, moles of the components may be different, but equivalents are always the same. And one more conclusion of this principle: number of equivalents is equal to number of moles into n factor. So based on the principle of gram equivalence, we can first estimate the n factor and immediately you can easily calculate the equivalent mass. This is the application part of equivalent mass, especially useful mainly in the case of advanced examination. And students, with this example, I am going to conclude this session. And in the next session, I will explain two more examples because very important approach. And then we will continue the journey of equivalent weight. Thank you.